Okay, so it's now time to look at magnetism. We talked about it a little bit before the lab, but I didn't want to say too much because I didn't want to give things away. I will post these notes in the course material folder, the handouts folder, but I would like to go through them. So today we already started talking about magnets and magnetism, and a few of the things that we said, I'm just going to recap. So one of the things that we said was that all magnets have a north and a south region. And even if you cut the magnet in half, the two parts will still have a north and a south region. If you cut it again and again and again, you will still keep getting tinier and tinier magnets with both a north and a south region. And one of the things is we have never been able to actually isolate one of the poles. So you'll hear the term monopole. We haven't been able to get a monopole. Magnets are always dipolar. Okay? That's unlike charges. We've been able to get a single charge, but we have not been able to get a single pole of a magnet. Just like charges, all magnets have magnetic fields around themselves. And today I couldn't show you what those fields look like because I didn't want to ruin the lab. But you now know that they look a lot like electric fields. Okay? We can show them. Oh, and so a magnetic field, the letter for magnetic field is a capital B. And it's measured in Teslas, named after Nikolai Tesla. And yes, I'm massacring his first name because I'm English. All right. So we can show the magnetic field using magnetic field lines. And magnetic field lines are exactly like electric field lines and gravitational field lines. They have all the same properties. What were those properties? Well, one, they show the direction of the force on an object at that point, and that direction is determined by the direction a compass will point when placed at that point in the field. Another property of the field lines is that they never cross, just like the electric ones don't. Another property of any kind of field lines, including magnetic, is that they show the strength of the field by their concentration, right? The more field lines, the stronger the field. So we would expect to see more field lines, a higher concentration of field lines closer to the magnet, right? They'd be closer together here by the ends of the magnet, and they'd be further apart the further you got away from the magnet. What you would have learned in the lab, and I hope that I'm not ruining it on anyone because I'm hoping everyone will have done the lab by the time they watch the video, is that the compass shows us that outside a magnet, the field lines go from north to south, outside the magnet. Okay? So this arrow would go this way, out of the north and into the south. The field lines are really closed loops. So inside, they actually go from south to north because they have to complete the loop. Okay, so but outside a magnet from north to south, and then inside a magnet, it would be south to north. There's one word that I didn't mention today, and it's called magnetic flux. Magnetic flux. And it's simply the number of field lines passing through a given area or a given surface. So it's the number of field lines passing through a surface or a given area. Surface area. So like if you think about it, right? Like if you have a sheet of paper, like how many field lines are going through this sheet of paper? So it's like field lines per area, or actually we talk about flux per area. And obviously the number of field lines per area should be proportional to the strength of the field, right? Because the stronger the field, the more field lines, and so the more field lines that would be going through an area. And so field, so flux is Webers per meter squared, field lines per area, will be equal to 1 Tesla. A Weber, Weber, is the measure of flux. We won't actually be calculating it. This would be like a multiple choice question. Like, what is magnetic flux measured in? And so the number of Webers per meter would give us a Tesla. Okay? One last little note is, and I hope you all know this, a compass like you use today is actually a magnet. It's a magnet that's suspended on a knife edge, right? And that's why I didn't want you tipping the compasses today. A magnet that's suspended on a knife edge and that swings around. The early magnets, the early compasses that they used in boats and stuff, they just hung them on a rope so that they were free to turn. Okay? All right. So that's the first intro to magnets. The only other thing, and it's also some notes, it's looking at magnetic materials. Okay? Magnetic materials. Really, if you think of chemistry, remember little electrons? Usually we drew them like this, and they have a spin. And really, a little electron is like a tiny little magnet. If you have a spin up, it's like north-south, spin down, south-north. And that's why when you put two electrons in an electron configuration in a shell, they have to be opposite, because the north wouldn't like the north. So little electrons are like little magnets. So then imagine that all material is made up of electrons. So if all material is made up of electrons, then all material could end up having magnetic properties. And so the magnetic properties of materials really depend on how are the electrons lined up. And so we categorize all materials into 3 categories. The first category is called diamagnetic substances. Diamagnetic substances. And these are going to be about how are the electrons aligned. Here, the magnetic field, so if every electron is like a little magnet, then every electron has a magnetic field around it. Okay? So in diamagnetic substances, the magnetic fields of the electrons balance each other out. So magnetic fields of E balance each other out. What that means is there's no net overall field. Okay, like they balance each other out. If these things were placed in an external magnetic field, if I took a diamagnetic substance and I put it between 2 magnets, I measured the field before I put it in, and then I measured the field after, the field will actually get weaker. So when placed in an external magnetic field, they make the field weaker. Okay? And if you were to take a diamagnetic substance and hold it near a North Pole, it would be weakly repelled by the North Pole. But if you took it and held it near a South Pole, it would also be weakly repelled by it. So it's weakly repelled by both poles of a magnet. Okay, so those, examples: copper, bismuth, nitrogen, water, salt, all noble gases. They are all diamagnetic substances. Okay, so copper, bismuth, nitrogen, water, salt, now converting to this hydrogen gas, and all noble gases are all diamagnetic substances. There's more, I was just giving you a list of some. Okay, the second type of material are called paramagnetic substances. Paramagnetic substances. Okay, these ones, the magnetic fields of the electrons temporarily align.